IMO 2021 International Mathematical Olympiad problem number 6. So let's see, the problem is what? Let m be greater number greater than equal to, be an integer, a be a finite set of not necessarily positive integers, and b1, b2, b3 to bm be subsets of a. Assume that for each k equals 1, 2 to m, the sum of the elements of bk is m to the k. Prove that a contains at least m half elements. So let's check the problem here. We can say a equals a1, a2 to an, and b1 to bm are subsets of a. So a1 equals a11, a12 to a1k1, b2 equals a21, a22 to a2k2, and bm equals am1, am2 to amkm. Sigma of b1 is sum of them. We define this function equals a11 plus a12 plus to a1k1 and equals m from the assumption of the problem. We are writing the assumption of the problem. Sigma b2 equals a21 to a2k2 equals m squared, and sigma bm equals am1 plus to amkm equals m to the m. Now look, when we see something like this, m squared mm, we can understand that it relates to base m, because for example in base 2 the value of the numbers, let me consider in the next page. For example, in base m, the first number from right, its value is 1, the next number is m, the next number is m squared. For example, if m equals 2, the value of this is 1, it is 2, it is 4. When m equals 10, the value of this is 1, 10, 100. And now we would we want to consider in base m this number. So but here, if you pay attention, it starts from m, but we know the values start from 1. So we can multiply this number with m, so the value would change to m, or maybe we can place a 0 here, so it should start from m. Now let's check. For at first I say consider that xm minus 1, xm minus 2 to x0 in base m, and xi, these xr are between, because they are in base m, are between 0 and m minus 1. So the smallest number is that all of them equals 0, so b then equals 0, and the largest number is when all of them equals m minus 1, m to the m minus 1. And if you pay attention, xi, if for example x0 has m cases, x1 m cases, if you multiply off all of them, they have m to the m cases, and b also is between 0 and m to the m minus 1, so b also can be m to the m cases. And if you it is not hard to prove that. For we can make each b, for example, when b equals 0, all of them must equal 0. If b equals 1, x0 is 1 and all of them 0. You can prove that easily by induction, that for each of xi, we have m to the m cases, we reach a unique number, like base 2. When you write, for example, let me write base 2 for you, 0 0 0 1 1 0 1 1. It is 0, it is 1, it is 2, it is 3. So we can consider all these 4 numbers, and 0 0 is 1, is 0 0 1 1 1 0 2 1 1 is 3. So for each string, if we consider it as a string, each of them is a unique number. Okay, so the proof is really easy by induction. Now we can assume this point. Now let's consider the rest of the solution. So this b equals x0 plus x1m plus x2m squared to xm minus 1m to the m minus 1. And if we multiply both sides by m, or as I said, we can consider a 0 here. So it would be x0m x1m squared to xm minus 1m to the m, because we know that we want to relate it to sigma of b1, which equals m. It starts from m. Now, we replace m with the sum of elements in B1 here. Sigma B1 of B1 equals m equals A11 to A1K1. So if we replace them, m equals A11, A12 plus A1K1, and x1 times m squared, we replace the sum of with sum of elements in B2. It equals A21 plus 2 A2K2 plus 2 plus xm minus 1 times am1 plus am2 plus 2 amkm. Okay, let me write m. Okay, so it was 1, 2, and for m minus 1 m amkm. Now if we factor, for example, from a1, maybe a1 is in some of them, for example in x11 to x1 s1. So a1 is, if we factor from a1, we have something like this, and it is greater than or equals 0, maybe we don't have anything, or less than, or maybe some of them are 0, and less than or equal. If a1 is in all of the parentheses, we know in each parenthesis we have at most one a1. So then it would be a1 times all of them, and the most, it is at most m times each of them equals m minus 1, so it is at most m times m minus 1. And also we can say it for all other things. So we know that B has exactly m to the m cases, from 0, and if you multiply B with m, again it has m to the m cases, because 0 would change to 0, 1 change to m, 2 change to 2m, so we have m to the m cases. And here we said all these coefficients are between 0 and m to the m minus 1, and maybe some of them are not reachable, so it is at most, each of them is m times m minus 1 plus 1 to the power of n, because we have n coefficients and each of them has these cases, and if if we consider them, each of them has this case, and if we consider all of them, it is to the power of n, and it is at most, mb has at most these cases. And we know that m times m minus 1 plus 1 is at most m squared. So m squared to the power of n, it is less than or equal that. So m to the m is less than or equal m to the 2n. So since their bases are equal, so we can say their powers, this power is less than or equal this power, and so m is less than or equal to n. So then we can conclude m half, if we divide both sides by 2, we can conclude m over 2 is less than or equal n. And that was the sentence of the problem, and we proved that.